Let's look at this integral, the integral of x squared times e to the x cubed dx. And I'm looking at, sure, let's just leave it as indefinite for the moment. Oh, let's fix this place. So, for this integral, when you see what I like to call a mixture of functions, meaning you have some sort of e to the something, or an x to a power, or a natural log of x, or a trig function, if you see words, if you see two of those things, we call it a mixture. I have x to a power and an exponential. And when you have what I like to call a mixture function, usually one of two methods is going to be the way to go. It's either going to be a u sub or integration by parts. And in my mind, I would always prefer it to be a u sub, because to me, u sub feels easier. So I'm always going to look to see, can I make this a u sub problem first? So if I was going to try a u sub here, I would make what I think of as the natural choice for u, which is to let u equal x cubed. Again, for two reasons. Reason one, it's stuck. It's in the exponent. Reason two, the better reason, its derivative is also in the integral. And I'm going to remind you all, we don't care about constant multiples. Constant multiples, that 3 is garbage. It's trash. It goes away. We can always deal with it. So if you're off by a multiple of 17, it's not a problem. Is that your question, Lilani? No. E is a constant. E is a constant. But it's e to a, but the thing is we have really e to the x cubed there, so that's a function. So I'm going to, so there's that, so I've been doing this a certain way because that's the way I like to do it. So the way I would do this is I would let du equal 3x squared times dx, and then I would divide both sides by 3 to say that 1/3 du equals x squared times dx. Because I see that my integral has an x squared times dx. So I would do this as e to the x cubed times x squared times dx. And then I would say, oh, x squared times dx, that's equal to my 1/3 times du. And x cubed, that's equal to u. So I can rewrite this integral as the integral of e to the u times 1/3 du, which I would then bring the 1/3 out in front. This is not the only way to do it. This is the way I like to do it. And I do think it's the best, but I'm not going to lie. I think it's the best. Of course, I think it's the best. It's the way I like to do it. But if you prefer, you can also do something like this. Instead of doing this, from this step here, you can just isolate dx and divide both sides by 3x squared and say du divided by 3x squared is equal to dx. And then when you do this integral of x squared times e to the x cubed times dx, you can just start off by replacing dx with du over 3x squared. Now, the thing I don't like about this is it just looks gross. I don't like having an integral that has x's and u's in it. That's my problem. The next step here is to cancel stuff. I'm going to say that x squared divided by x squared cancels out. Is equal to 1. So now this integral is equal to the integral of e to the x cubed times du over 3. Does anyone see a problem about my integral and the variables it has in it? Right, exactly, because I can't have u's and x's. I need to have just u's or just x's, and I'm trying to get to u's. So exactly, I need to finish the process of transforming this and say, oh, that's my u. So this is really equal to, that's the wrong pen, the integral of e to the u times du over 3, or as I would prefer to write, 1/3 times the integral of e to the u du. Notice that either way I slice it, I still end up at the same integral, 1/3 integral of e to the u du. Question or just
So E is a constant. Okay, wait.
because E is a constant, but E to the X is a function of X. E to the U is a function of U. E to the something with variables in it is not a constant. Because depending on the value of X, that thing will change.
Yeah, exactly. So if that's the case, why didn't you assign that to you?
We could have made that choice. That's not the choice I want to make, though. So it is true, this problem you could have done by letting U equal E to the X cubed. But it's usually easier and more in your interest to make a simpler choice for you, to choose the thing that is just in the exponent as opposed to E to the thing in the exponent. That's really why. Yeah. So either way, we're going to get 1/3. Okay, what's the integral of E to the U? E to the U. But then since it's an indefinite integral, we have to then finish off by substituting back in what U was equal to. We picked U equal to X cubed. So our final answer here is 1/3 E to the X cubed plus C. That is the actual antiderivative or indefinite integral of X squared E to the X cubed. Okay. In contrast, let's look at this integral that looks very similar, but is not at all. Let's look at the integral of X squared times E to the 3X. Question.
Like we said, we had X squared times sin of X or sine of X.
Sine of X, yeah.
Couldn't you just like make U equal like X and then like
you'd have to let U equal X squared if it was X squared times sine of X. Well, actually,
saying, like, you know how like when you do the U is supposed to be like whatever in parentheses or whatever.
Yeah. Like if I had this.
Yeah, and then I made like UX.
So here's the problem, and I'll show you, but I'm just going to tell you point blank. If you're doing a U sub, and you just let U equal X, you're really not doing anything at all. Let me show you what I mean. If we chose U equal to X here, what's my derivative of U going to be? What's the derivative of X? So then du is equal to dx, right? So if I start changing this to u's, okay, well, dx becomes du, x becomes u, and x squared becomes u squared. So here's my new integral. It's the integral of u squared times sine of u times du. Oh, sorry. All I've really done is change the name of X to U, but it's still just as complicated as it was before. So when you're doing a U sub, you actually never want to let U equal X because you're just going to make yourself go in circles. You're going to get back to where you started without having done anything. On the other hand, and this is an important contrast, if you're doing integration by parts, it is perfectly okay to let U equal X because you're going to let dv equal to it. It's a very different process. So integration by parts is very different. It's okay to let U equal X. So for this problem here, this is not a U substitution problem. If I tried doing U sub, the only real choice here for U would be U equal to 3x. But then my du is 3 times dx. And not that I don't have that, but I still have this x squared over here left to deal with. That's problematic. This is an integration by parts problem. Now, unfortunately, it's actually an integration by parts twice problem, but we'll get there when we get there. So when you're doing integration by parts, there's a really kind of useful way of knowing how to choose what your U is going to equal. There's an acronym, and it's LATE. Technically, it's LIATE because there's inverse trig as well, but almost never do we see inverse trig in this class with one small exception. So I'm going to leave it at this and we'll adjust if we need to. So the way you pick U is first you look for anything that is a logarithm. Do I have any logarithms? I do not. So then if you don't have any logarithms, you pick U to be any power of X. or whatever your variable is. I have that here. I have an x squared. So in this problem, we are going to let u equal x squared. But if we didn't have that, we would let u equal a trig function. And we kind of just write e at the end to finish off the acronym. We almost never let u equal e to the x. Right, if you're doing integration by parts, letting u equal an exponential function is almost never the right choice. So here we're letting u equal x squared. And then once you've decided what u is, which always sounds wrong when I say it, it sounds like I'm saying something with poor grammar. dv is automatically decided for you. You get no choices after you pick u. dv is the rest. So my dv is going to be e to the 3x dx. I need du and I need v. du is the derivative of x squared, which is 2x times dx. I should really say du is the derivative of x squared times dx because we bring the dx over. v is the antiderivative of e to the 3x, which I know is, and this is actually why I mentioned the mini u substitutions a few classes ago. When you anti-differentiate e to the 3x, you don't want to have to do another integral with u substitution on its own. We want to be able to say, oh, the antiderivative of e to the 3x is e to the 3x divided by 3. Because we know that if we multiplied by 3, we know that if we took the derivative, we would multiply by 3. So the antiderivative, we have to divide by that same constant. Also, if you took the derivative of this, the derivative of e to the 3x is e to the 3x times 3. And the 3 and the 1/3 would cancel, getting us back to e to the 3x thing. Questions about that particular thing? I'm happy to say more about it. I'm going to say more anyway. So here's what I'm really saying. If I want to find the integral of e to the 3x, the long way of doing this is making a u sub and saying u equals 3x. du equals 3 times dx. 1/3 times du equals dx. Then I rewrite the integral as well. dx is equal to 1/3 du. 3x is equal to u. So this becomes the integral of e to the u times 1/3 du. That constant multiple that's not being raised to a power gets to come out in front. And the integral of e to the u, once again, is e to the u. So you get 1/3 e to the u. I don't care about the plus c because it's just side work. And then I'm going to plug back in u, which is equal to 3x. So when you integrate or anti-differentiate e to the 3x, you get e to the 3x divided by 3. And it doesn't matter, right? That could have been 3 or 30 or 5 or 15 or any constant. You're still going to end up dividing by that same constant when you anti-differentiate e to the something times x. So very so that's why I'm doing this so kind of quickly. So they don't want to do this work every time. So now we have to remember the formula. Oh, I didn't say the fun thing last time. So when you do integration by parts, when you pick your u and your dv, the integral of u dv is, are you ready for it? Yeah. Okay, someone knows. Ultraviolet, super voodoo. UV, ultraviolet, minus the integral super VDU, voodoo. It's hard to forget once you've heard it a couple times. Kind of like I tan and get sexy. You guys know that one? Oh, you don't know I tan and get sexy. Wow, we'll get there in a minute. I don't tan, but still it's a great thing. So here, our integral of u dv is going to equal u times v. So x squared times 1/3 e to the 3x minus the integral of v du, which is 1/3 e to the 3x times 2x dx. Now here's the bad news. We have to do integration by parts again. It's not that bad though, I promise. So I'm going to rewrite this just a little bit. I'm going to rewrite this as 1/3 x squared times e to the 3x. And the 1/3 times 2, I'm going to bring out in front of this integral and write it as minus 2/3 times the integral of x times e to the 3x. And so now I'm going to do an integration by parts again. I'm going to let u equal any power of x, and my dv is going to be the rest. Of course, I've run out of room on this piece of paper. I'll write it again. So similar choices here. Our u is going to equal x. Our dv is going to be just like it was before, e to the 3x times dx. The derivative, or I should say our du is equal to the derivative of x times dx. And our v is once again the antiderivative of e to the 3x, which is 1/3 e to the 3x. For the same reason it was over here. And now, writing the entire expression out, I get 1/3 times x squared times e to the 3x minus 2/3 times the entire integral of u dv. But the entire integral of u dv is all of uv minus the integral of v du. So this minus 2/3 has to multiply by the entire ultraviolet super voodoo. So I'm going to get uv, so x times 1/3 e to the 3x minus the integral of v du, sorry, 1/3 e to the 3x dx. And now we're almost done. Don't worry, I'm going to show you a shorter way to do a problem like this. If you think this looks terrible and long, it is kind of terrible and long, but there is a faster way. So two things at once here. Two things at once? No, one thing at once. I got 1/3 x squared e to the 3x minus 2/3 times 1/3 x e to the 3x. And the integral of 1/3 e to the 3x is 1/3 e to the 3x divided by 3, because the antiderivative of e to the 3x one more time is 1/3 e to the 3x. So a lot of times with this repeated integration by parts, you're doing the same antiderivative over and over again. We did the antiderivative of e to the 3x 3 times here. Now I should write plus c because I don't have any more integral symbols and it's indefinite. And then finally, you could leave it like this. I would prefer to distribute the negative 2/3 and write it as 1/3 x squared e to the 3x minus 2/3 times 1/3 is minus 2/9 times x times e to the 3x. And minus 2/3 times minus 1/3 times 1/3 is going to be positive 2 over 3 times 3 times 3, which is 27 e to the 3x. Wow, fun times. Okay. Questions about any of the steps along the way here? I'm not going to show you the short way just yet, but I promise you before the end of the class today, I'll show you the shorter way of doing this problem. I just want to show you a few more examples before we get there. I know, I'm sorry. I'm a knuckle popper. Danny, you look like you have a question. Okay, it's all right.
So when you go from like that part when you start the new page onto like the next part, are you like you're just redoing the
I'm doing integration by parts again.
Okay.
Because this new integral is still a mixture. It's still x to a power, x to the first, times an exponential thing. And so I'm doing the same sort of thing. I'm saying, oh, well, if I'm going to do, I don't know how to integrate that.
So you just leave the first part alone and you just add the second part alone?
When you say, well, I'm not sure what you mean by that.
Like, you know how you have the, okay, you have to circle that square, and you have that part before that, you just leave that, and then you do the part 5.
So like in the beginning here, when I was doing this integral, I made u equal to the x squared part. Again, when you're doing integration by parts, which you're usually doing because you have a mixture of functions multiplied together, you're typically saying, I'm going to pick u to be the thing that when I take its derivative, it gets simpler. The derivative of x squared is 2x, and we consider that to be a simpler thing. And the hope is that the thing you're left with for dv, when you anti-differentiate it, it doesn't really get more complicated. The antiderivative of e to the 3x is essentially still e to the 3x. Yeah, there's a coefficient of 1/3. That doesn't really change its complexity. So that's why we're making those choices. And then we're using this formula to rewrite the integral of u times dv as u times v minus the integral of v times du. And the point of this is that this new integral is easier to integrate. But sometimes easier means you still have to do integration by parts again. So I factored out the 2 times 1/3, and I was left with an x times e to the 3x. My power of x got 1 less, which says to me if I do this again, the power of x is probably going to be even 1 less again. So in the next iteration, I'm probably going to end up with x to the 0, so no x's, times e to the 3x, which I do. When I do this again, sorry, papers, come on, papers. I end up with, after all is said and done, in the next step here, my integral of u dv is once again u times v minus the integral of v times du. But my new integral here is actually something I am capable of integrating without employing any other processes. So that's what I do. So it's kind of like a reduction. We'll just keep on working on it until we get to something we know how to deal with. Let's look at another example that doesn't require so many steps. Now let's see. Where are you? Other example? Yeah, like yeah, sure. You're good. You're fine. So again, I really do like the contrast between integration by parts and u substitution. So let's look at something that's actually going to be a u substitution first. Let's say I have the integral of the natural log of x raised to the 3rd power over x. And let's go ahead and make it a, no, I feel like it, yeah, sure. Let's make it a definite integral from 1 to e. Cool. So what seems like a plausible choice for a u sub here? Yeah. And again, it's meeting all of our requirements. It's stuck inside being raised to the 3rd power. And more importantly, its derivative is 1 over x. So du is equal to 1 over x times dx. And I will point out, we exactly have a 1 over x times dx. You could write it out that way. I don't think you need to. I think it's fine to just say you've got 1 over x times dx, and that's equal to du. But if it's more comfortable, write it out the long way and say this is the integral of from 1 to e of the natural log of x cubed times 1 over x dx to make it more obvious that, oh yeah, that's my du. There's my u. So I can rewrite this integral as the integral of u cubed times du. It couldn't be much better than that for a u sub. I should change my limits of integration here. So if x equals 1, u is going to equal the natural log of 1. We could write the natural log of 1 if we didn't know what that was, but it is important that we know that the natural log of 1 is 0. And similarly, if x equals e, u is going to equal the natural log of e, which is equal to 1. So we're almost done. We get u to the 4th over 4 from 0 to 1. We plug in 1, we get 1 to the 4th, which is 1 over 4. We plug in 0, we get 0 to the 4th, which is 0 over 4. And 1/4 minus 0 is just 1/4. I will point out that if we had not done a definite integral, if it was indefinite, our antiderivative of the natural log of x cubed over x would have been u to the 4th over 4, but then we would have to plug back in the natural log of x, and we would have gotten natural log of x to the 4th over 4 plus c, just to kind of point that out. Question, Alani, or just stretching? Cool. All right. Let's contrast with the integral of the natural log of x over x cubed. They look not that dissimilar. I mean, they are pretty dissimilar, but they look, someone could try to fool you into thinking they were the same. Here, there isn't a good choice for a U substitution. Actually, it's not that there isn't a good choice, it's that the choice is not going to work out. If you were to let U equal the natural log of X, we'll pretend like we're going to do over here. If U is the natural log of X, your du is still 1 over X dx. And if you write this integral, I can write it as the natural log of X over X squared times 1 over X dx. The 1 over X dx is certainly a du. The natural log of X is a u, but then X squared is this. If I really tried to work hard and do a back substitution, I could solve this for X and say that e to the u is equal to X. So that's going to be e to the u squared. That seems terrible. I don't want to integrate e over e to the u squared. That seems like really hard. It seems like something that would probably require integration by parts, to be honest. But if you do a u sub and it requires integration by parts after that, you might have just been better off trying integration by parts from the get-go. So here, we're going to try integration by parts. And I see a natural log of X, and that is always the choice you want to pick for u if you're doing integration by parts and you have one. We're going to let u equal natural log of X. All right, I want everyone to try on their own writing down what dv has to equal. Don't tell me, just write it down. Give you like 30 seconds. What am I? Yeah.
So when you do the u and dv like twice, that second time will it always be the same like dv?
Not always, but often, yes. I would say a better way to think of it is dv will be the same type of thing. So if in your first integral, in your first integration by parts, like u was x cubed and dv was sine, then in your next integral, your u will still probably be some power of x, and your dv will still probably be some trig function, but it'll probably be cosine.
Yeah.
So the things are the same types of things, not exactly the same thing every time. So looking at this one, if dv is natural log of x, sorry, if u is natural log of x, dv is everything that is multiplying it. So that's going to be 1 over x cubed times dx. Or preferably, since I know I'm going to have to integrate it, I should really write that as x to the negative third times dx. So now I need to find the rest. The derivative of the natural log of x is just 1 over x. So du is 1 over x times dx. And v is the antiderivative of x to the negative third. So it's x to the negative 2 divided by negative 2. Which you might simplify as negative bless you 1 over 2x squared. Oh, I forgot to talk about I can't get sexy. We'll get time. Don't worry. It's not that exciting, I promise. So then I've got my u, my v, my dv, my du. So this integral is equal to, what's the formula? What's the thing we say? Say it with me. Come on, it's one time. Yeah. Okay. On 3. Everybody ready? 1, 2, 3. Ultraviolet super voodoo. So that's our uv minus the integral of vd. You're not actually going to write that. I mean, you can underneath, but you're actually just writing the things you have found u and v and du equal to. So u is the natural log of x. V is our x to the negative second over negative 2. Sorry, I think you're getting a little bit small over here. And then minus the integral of v again is x to the negative second over negative 2. Du is 1 over x times dx. The whole point of integration by parts is that the new integral here is simpler. It's easier to actually anti-differentiate. And this is as long as we take the time to actually simplify it first. So rewriting this, and I'm going to rewrite this as negative 1 over 2x squared times natural log of x, because I don't know, I just prefer to write it that way. I'm going to bring out the negative 1/2 here. So minus a negative 1/2 is plus 1/2. Then I have the integral of x to the negative second divided by x. And I can put those two together and get x to the negative third. Because x to the negative second divided by x to the first, we subtract those powers, and negative 2 minus 1 is negative 3. So that's the antiderivative of x to the negative 3. I brought out the negative 1/2. If you prefer, you could rewrite this integral first as the integral of negative 1/2 times x to the negative second, and 1 over x is the same as x to the negative first. And then x to the negative second times x to the negative first is x to the negative third, because we're adding those powers. You like it that way better. In either case, now I'm going to anti-differentiate this part here, and I'm going to get, I should probably just write this as one fraction. I could write that as negative natural log of x over 2x squared, just to save space, plus 1/2. The antiderivative of x to the negative third is something I already did and got x to the negative 2 over negative 2. Plus c. Yes, we could make this look nicer, but I ran out of space and I don't want to. But you can make that negative 1 over 4x squared if you prefer. I probably prefer. But whatever. So, integration by parts, you're looking for things that multiply together. You're trying to figure out what to pick for you so that it gets simpler. We definitely think that 1 over x is a simpler thing than u equal to natural log of x. So the differentiating the natural log made it a simpler thing to deal with. And anti-differentiating x to the negative third, getting x to the negative second, it's not really more complicated. Okay. Sorry, say that one more time. Where? Right here. So when you anti-differentiate this, what, right? Cool. Okay. So I promised you a couple things, and as always, time is running short in this class because it just is. So first of all, just as a real quick aside, I tend to get sexy is just the, how I remember the trig identity, 1 plus tangent squared of x is equal to secant squared of x. It's not that exciting, but it is unforgettable. Almost as good as all strippers take cash. All students take calculus, all strippers take cash.
Wait, all this crazy.
You're like, that one we're going to remember. All strippers take cash is how you remember which trig functions are positive and which quadrants. Okay, so, but the other thing I promised you is actually more interesting, or maybe not more interesting, but more useful for this class. So, let's say I wanted you to find the antiderivative of x cubed times cosine of x. And the bad news here is that doing this integral requires integration by parts, not 1, not 2, but 3 times, which is trash. Here's the silver lining. For integrals like this, this only works for 3 types of integrals. For x to a power times cosine. It also works for x to a power times sine, or x to a positive integer power times e to the x. And you can throw in some constants as well. It could be like sine of 2x, or e to the 5x, or cosine of 6x, or whatever. But it's got to be, and really you can actually have a polynomial, like you could have x to the 4th plus 2x squared plus 1 all times cosine or sine of e to the x. But the basic thing is this. So here's how this works. And instead of doing these 3 integration by parts, what would we choose for you in the beginning here if we were making a choice? Would I pick u equal to x cubed, or I pick u equal to cosine of x? Think about the late acronym. I don't have a logarithm. What's the next thing I look for? Any power of x, meaning x to the whatever. In this case, x to the 3rd. So our u would be x cubed. And now you're going to make a list of all the derivatives of your choice of u until you get to 0. That's why your u has to be x to a positive integer power of x. Because any other power, you won't get to 0 eventually. The derivative of x cubed is, the derivative of 3x squared is, the derivative of 6x is, and the derivative of 6 is, we got to 0. Yay. On the other, so on this side, you take all the derivatives. Differentiate your u. Just like you normally do when you do integration by parts. You start with u and you find du, your derivative of u. In the other column are dv. Well, dv is easy. It's just cosine of x times dx. Now, I'm not going to write the dx part because we just typically don't work doing this method called tabular integration because we're just using a table. So in the other direction, antiderivatives. So what's the antiderivative of cosine? Is it positive sign or is it negative sign? Positive sign. What's the antiderivative of positive sign? Negative cosine. Antiderivative of negative cosine? Negative sign. And antiderivative of negative sign gets you back to positive cosine. Where's my green pen? Okay, so here's what we get. Here is the actual answer that we're going to write out. It's going to be plus x cubed times sine of x minus 3x squared times negative cosine plus 6x times negative sine minus 6 times cosine. It is always starting with plus, plus, minus, plus, minus, plus, minus, plus, minus, plus, minus, and then you're just doing the plus of this product, the minus of this product, the plus of that product, the minus of this product. So writing this out, the integral of x cubed times cosine of x dx is equal to positive x cubed times sine of x minus 3x squared times negative cosine of x plus 6x times negative sine of x minus 6 times cosine of x. And what do I need at the end? Plus c. Now, of course, we should be a little bit more smart about this and simplify the signs along the way. I should have really written this as just x cubed times sine of x minus times a minus is plus 3x squared times cosine of x minus 6x sine of x minus 6 cosine of x. Let's see. And this tabular method of integration, this is called tabular integration because you're using a table to do it, will always work for integrals of this variety. X to a positive integer power times cosine, or x to a positive integer times sine, or x to a positive integer power times d to the x. To backtrack a little bit, if we look back at that first integration by parts we did, which was the integral of x squared times e to the 3x, we could have used tabular integration for that as well. Let's see how. So for the integral of x squared times e to the 3x dx, for this one, my choice of u would have also been x to a power. Then the derivatives are going to be 2x, 2, and 0. My choice for dv would have been e to the 3x. My antiderivatives are e to the 3x divided by 3, and then again divided by 3, and then again divided by 3. Every time I anti-differentiate e to the 3x, I get another multiple of 1/3. So then my answer is going to be plus, minus, plus. So doing this the fast way, we end up getting that this is equal to 1/3 x squared e to the 3x minus 2 times 1/9 is 2/9 x e to the 3x. 2 times 1/27 is plus 2/27 e to the 3x plus c. And if we look back to where our answer is, wherever it may be, that is a, can you see? You cannot see. Here, there it is. That is exactly the same as the answer we got before. pretty slick. So this is something that's nice that most professors are super okay with people using.
Why do you not use-
Well, because we don't, so if you look back at one of the previous problems we did, we don't actually use dv. Right? Right, because the formula, right, if you do the integral of u dv, the answer is u times v minus the integral of v du, and the dv doesn't get used. That's why. Good question. Okay. Oh, there's one other thing. Yeah, there's one other terrible example I should show you, and I guess we'll have to. Yeah. So let's make it slightly terrible, but not too terrible. Let's say we want to find the integral of e to the 2x times sine of x. I know some of you, at least in most of the classes I've seen the lecture notes for, an example like this has been shown. I think it was, for most of you, it was e to the x times cosine. For this style of integral in particular, there is one and only one way of doing, well, okay, that's not entirely true. There is a method that works where you have to do integration by parts twice. Technically, you can make either choice you want. What I mean by either choice is, for this here, you could pick u equal to sine and dv equal to e to the 2x. You could also make the reverse choice. But since I have said we have this acronym LATE, L-A-T-E, where we pick u equal to a log, or then a power of x, or then a trig function, I should follow the thing I've said and pick u equal to the trig function here. So I'm going to pick u equal to sine of x. And then dv is the rest. It's e to the 2x dx. How much time have we got? Okay. I want you all to write down both what du is equal to and what v is equal to. We're for sure going to run out of space here, so I just break big. Yes, we'll talk about partial fractions on Monday because we've run out of time. I do have older videos, by the way. If you're looking, if you need like other content, you can go look at my 17B playlist from previous quarters, and there should somewhere be partial fractions on there from like, a month into whatever last time I thought it was. And also, I think I've labeled them pretty decently, at least from the last time I taught it. So you can also just read the titles, and it should say like partial fractions. You could probably even like search, right? Like there's a search bar, and you could use the internet appropriately. All right, so our du was what? Not everybody at once. What's the derivative of sine? Dx. And our v was, is it e to the 2x times 2, or is it e to the 2x divided by 2? Right, e to the 2x divided by 2. Or if you prefer, 1/2 times e to the 2x, which is probably what I would actually write. So my u times v is going to be 1/2 e to the 2x times sine of x. Yes, I know I wrote v times u instead of u times v. It doesn't matter what order you multiply things in. Minus the integral of v du is 1/2 e to the 2x times cosine of x. And you might see that we're essentially back at a very similar place. I'm going to bring out the 1/2 in front of the integral, but I'm essentially at another e to the 2x times cosine now instead of sine. This is the stage where you have to make sure you do the right thing. So at this point here, you have to follow the pattern you've already used, meaning if you chose u to be the trig thing and dv to be the exponential thing, you have to make the same choice when you do integration of parts again. If you make the opposite choice, you'll end up undoing the work you've done, and you'll end up with e to the integral of e to the 2x sine of x is equal to the integral of e to the 2x sine of x, which is true and not at all helpful. So here we're going to make now the choice that u is equal to cosine of x. And I should write the integral again because, sure. So u is equal to cosine of x. dv is equal to e to the 2x dx. Our du is negative sine of x dx. And v is equal to 1/2 e to the 2x once again. So now here's what we've got. I'm gonna write the whole thing out. The integral of e to the 2x sine of x is equal to 1/2 e to the 2x sine of x minus 1/2 times the integral of e to the 2x times cosine of x dx. I'm just writing the same thing I wrote before. And now I'm going to rewrite this as 1/2 e to the 2x sine of x minus 1/2. Okay, the integral of this, well, again, there's my u. There's my dv, and the integral of u dv is going to be u times v. So 1/2 e to the 2x times cosine of x minus the integral of v times du. 1/2 e to the 2x times negative sine of x dx. We're almost done with this problem, I promise. We can finish it in the next minute and a half here. So I'm going to distribute here, and I'm going to be super careful. Get the integral of e to the 2x sine of x dx equal to 1/2 e to the 2x times sine of x minus 1/2 times 1/2 is minus 1/4 e to the 2x times cosine of x. And the minus, so watch here, watch extra closely. The minus 1/2 times minus 1/2 times minus 1 is a minus, right, because the minus 1/4. And then I've still got the integral of e to the 2x sine of x. Yeah, I'll make sure everyone's cool with that. I took this negative 1/2, I distributed it here, great. I distributed it there. And the minus 1/2 times the minus 1 times the minus, or 1/2 minus 1, whatever, is negative 1/4. And now we've gotten back to the integral we started with. The integral of e to the 2x sine of x. So now we do the thing that always felt like was cheating when I learned this the first time, is we're going to add that to both sides. I'm going to add 1/4 integral of e to the 2x sine of x to the right side and to the left side. Now I'll point out that we have 1 times the integral of e to the 2x sine of x plus 1/4 times the integral of e to the 2x sine of x, sine of 2x. Oh, sine of x. Sorry, I wrote 2x there. That's terrible. Sorry. What's 1 of something plus 1/4 of something? I mean, you could just literally say 1 and 1/4 or 1.25, but I would prefer to use the fraction 5/4. So when I add these two integrals together, I get 5/4 of the integral of e to the 2x times sine of x dx. And that's equal to just this, 1/2 e to the 2x sine of x minus 1/4 e to the 2x cosine of x. And then to get rid of the 5/4, I multiply both sides by 4/5. So that finally I can say the integral of e to the 2x sine of x dx is equal to 4/5 times 1/2 e to the 2x sine of x. Sorry, you can't see that, apologies. Minus 1/4 e to the 2x cosine of x. Plus c. And that is actually the answer. It feels kind of weird because it feels like you didn't actually really ever find the antiderivative, but you totally did. If you take the derivative of all this, using the product rule and the chain rule a couple times, and simplifying it down, you will get back to exactly e to the 2x sine of x. And that is how you usually, that is always the process for anti-differentiating, like e to the x times sine of x or e to the x times cosine of x. It's always this process of integration by parts twice, and then getting back the thing you started with and adding it back over to the other side, and then dividing by whatever the coefficient is, or multiplying by the coefficient. All right, I should stop talking. It's 3:02. Have a lovely weekend.